We're going to do normal curve operations using the powers of the central limit theorem in order to find confidence intervals with our sample averages. Here is the normal curve, and we want to figure out what z-scores make up the middle 90%, 95%, and 99%, the most common sizes of confidence intervals on the normal curve. So we need to figure out what are those z-scores. If you remember from a previous section, we had these particular values of something we called z-star, 1.645, 1.960, and 2.576. And let's just refresh ourselves on what that all means. If we want to figure out the area under the curve between, let's say, negative 1.645 and positive 1.645, so that would be around here, negative 1.645 and then positive 1.645, we would go to our calculator and do normal CDF, and we would just type in those two values right away, negative and then the positive version. And what we'll find is the area under the curve in between those is almost exactly 90%, or 0.90. So the area between these two red numbers is going to be about 90%. Same idea if we were to plug in negative 1.96 to 1.96, we're going to get about 95% of the curve, the middle of the curve in between those values. And then if we were to do the same thing over here with negative 2.576 and positive 2.576 from here all the way back to here, that's going to give us 99% of the area under the normal curve. So what these z-star values allow us to do is make predictions on where our data is most likely to fall. If you remember the z-score equation, it says that z is equal to our value of interest x minus our mean divided by the standard deviation sigma. What we're going to do is do a little bit of manipulation to solve for mu, make a few little substitutions, and see if we can derive how confidence intervals are found. So the first thing we're going to do is multiply both sides by the standard deviation. And if we do that, that's going to end up canceling this out of our denominator here. Next thing we're going to do is add mu to both sides. We're going to go ahead and add mu to both sides, because I like working with positive numbers. So we add mu to both sides here, and now, since we're solving for mu, we're going to want to subtract this sigma z from both sides. So we'll subtract sigma z from both sides. I'll just move it over here, put a little minus sign in front, and then we're left with mu on the other side, just by itself. So we'll clean that up. And if I wanted to have maybe a better view of what this is like, I'm going to go ahead and slide this here. You'll notice I made a slight substitution, and I put in x bar for x here. And because we're looking at sampling distributions, we're going to assume that our value of interest is actually x bar, not just x. And we still have mu and sigma, so we're not used to seeing these things all together in the same equation, but let's go with it for a second and see where it gets us. One of the things we talked about on the previous slide here was looking at these z-scores that allow us to find the middle 90, 95, and 99%. And we said we called that value z-star. So let's go ahead and call that z-star down here too. So our z is now z-star. It's still just a z-score. And one of the things about z-star is it implies that it's the positive and the negative, so it goes both ways. We're finding a confidence interval. So we're going to replace this negative sign with plus or minus. And the last little substitution I'm going to make is, since we're using the central limit theorem, we don't just have sigma, we're dividing our standard deviation by the square root of the sample size. So we're going to use sigma divided by the square root of n. So if you take this whole thing here that we just slowly derived, clean it up, it's going to look like this. Our mean is equal to our estimate of the mean x bar plus or minus the standard deviation divided by the square root of n times z star. Now that's a lot to take in, so let's break it down one piece at a time. First of all, the thing that we are trying to find here on the other side of the equation, mu, is the mean of the entire population. Now, since we usually don't know this, we're not going to give a single number. We're going to give this as a range, as a confidence interval. I'm X% confident that it falls between here and here. So that's what we're going to try to solve for, is mu. In green over here, X bar is the mean of the sample. So let's say we have a sample of 50 people that we collected data from. I would take those 50 values and average them together, and that would be my X bar. Sigma here in red is the standard deviation of the entire population. Now, we don't know the mean of the whole population. In reality, we're usually not going to know the mean or the standard deviation of the entire population either. But for the moment, we're going to just assume that we do, and we'll figure out how to replace that later with the t-curve. But assuming we're using the standard normal curve, let's assume that we know this population standard deviation. Z star is the z-score for the given confidence interval. So if we're doing 90% interval, we're looking at 1.645 and so forth. And then finally in pink here, n is our sample size. So we said in that little example, if we had a sample size of 50, we would average the values together to get our X bar. N would be 50, our sample size. Now if you look at this equation, what it implies is that when you're trying to predict what mu is, when you're trying to predict the population mean, there's always going to be an error range. It's going to be plus or minus, it's going to be your best guess here, X bar, plus or minus this error. And you're never going to be 100% confident in getting that error down to 0. But there are some ways that you can reduce it. The standard deviation is what it is. We can't do anything about that. But we can change Z star and we can change n. So the way that you can decrease your error range, the first way, is to just be less confident. Well, if I'm only 10% confident, I can give you a pretty darn precise guess of what the mean's going to be, because there's a 90% chance I'll be wrong. But if I want to be really confident, if I want to be 99% confident, then my z-star gets to be pretty big. We said just a moment ago z-star is 2.576. We want to be 99% confident. But if I'm willing to sacrifice some confidence and go down to 90%, I can shrink that number from 2.576 all the way down to 1.645. The whole point here is that if you are less confident, you will have a smaller range, a smaller amount of error in your confidence interval. The other way, that's a much more, I guess, productive way to reduce error, is to increase your sample size. Because there you don't have to give up any confidence. You can still be 95, 99% confident in your answer, and if you get a bigger sample size, you're going to decrease your error. So instead of asking 20, 30, 40 people to be in your sample, if you ask 800, you're going to really get that error down to something very meaningful. Let's do a practice problem with it. You took a simple random sample of student heights at BHS. Height is known to be normally distributed with a standard deviation of 2.5 inches. So we're assuming that we know the population standard deviation here, and it's 2.5 inches. I'm going to label that sigma right away. A sample of 25 students, label that right away again, n is our sample size. A sample of 25 students yielded a mean of 66 inches. Since this mean right here is from a sample, I'm going to call that X bar. That's not mu. We don't know the whole population's standard deviation or mean. We only know our data, our mean from the sample. So we want to find the population mean with 95% confidence. Now, instead of memorizing that formula, we're going to go ahead and pull that from our reference sheet here. And that's going to be mu is equal to X bar plus or minus all of this stuff right here. First thing I'm going to do is start plugging in those values, because I believe I know X bar right here, 66 inches, sigma 2.5, I know n is 25, and z star, well, I want to be 95% confident in my answer here. I'll just move that to purple. 95% confident in my answer, so that's going to translate to a z-score of 1.960. So z star is going to be that right there. So let's plug it all in. Mu is equal to 66 plus or minus my standard deviation 2.5 of the whole population, and I want to update that with the central limit theorem by dividing it by the square root of 25 and then multiplying that all by z star, which in this case is 1.96. And now usually when I'm doing this in my calculator, the only part that I'm going to type into my calculator is this part right here. Because then when I write it, I'll write it as 66 plus or minus whatever this turns out to be. So when I do that, I do 2.5. I can multiply straight across the top 1 times 1.96 and then divide by the square root of 25. Divided by the square root of 25. And it says it equals 0.98. So this error right here is equal to 0.98. So that means my final estimate would be that mu is equal to 66 plus or minus 0.98. Now there are other ways to express this interval, and we'll talk about converting it to different forms later. But this here would be your basic confidence interval using that standard equation that we just talked about.